Okay, so hello to everyone. I'm Paul. I'm a PhD student in the lab of Bela Novak, and I'm looking forward to a combined conference with interesting talks and discussions. And my contribution will be interfacing SBML and CellML with the scientific machine learning and constraint-based modeling systems in Julia. But first, let me tell you how I got interested and why I got interested in the Julia programming language. So the Julia programming language tries to kind of combine the best of two worlds, and the one world being high performance languages like C, the other world being high level programming languages like Python. And Julia is a general purpose programming language that is just in time compiled, uses a dynamical type system, but optionally allows you to specify your types, which in turn allows you to do things like multiple dispatch. I think the major advantages of Julia are that it's open source and free, and it's specifically designed for computational sciences. And I think this is best reflected by three attributes. So Julia is fast. Here on the right-hand side, can you see my cursor at all?
Yes, we see the mouse.
Yes. Yeah, excellent. So on the right-hand side here, you can see a benchmark for a stiff ODE problem, and the Julia solvers are very competitive in this benchmark. Julia is also high level for easy prototyping of code, and this makes it also possible for scientists like me who are not specifically very quantitative sciences to pick up the language. Then finally, Julia is also developed for parallel and distributed computing, and I'll come to that in a bit later. Major disadvantages are coming from Julia being a very new programming language. There are not that many packages yet. It's still quickly evolving, which can make it a bit difficult to keep up the pace. And it doesn't have that many tutorials as compared to Python, for instance. Within Julia, there's then the scientific machine learning ecosystem that comprises several tools, for instance, ModelingToolkit for symbolic-numeric optimizations, differential equations.jl, which contains high-performance solvers for differential equations, and diffecflux, which contains optimizers for universal and neurodifferential equations, and tools for sensitivity analysis. There's also a bunch of more specialized packages, and I think this in total makes Julia very interesting for computational systems biologists. The big problem here, though, is that up until recently, there was no way to easily import your SBML or CellML models into the Julia programming language. And that I thought is a big issue, and kind of when the pandemic delayed my project, my main PhD project on the experimental side, I decided, okay, I'll try to create an importer for SBML models into Julia. And via GitHub, I met a bunch of other people who had the same idea, and together we developed a set of 3 different tools: SBML.jl, SBMLToolkit.jl, and CellMLToolkit.jl. So SBML.jl is just a parser that parses SBML models into a Julia struct, and that can then be used by COBRA for constraint-based modeling. SBMLToolkit takes this Julia struct and converts it into a ModelingToolkit reaction system, where ModelingToolkit is kind of the entry point into the whole scientific machine learning ecosystem in Julia. CellMLToolkit has its own parser and directly converts CellML models into ModelingToolkit ODE systems. In this presentation, I would highlight how you can use these importers that give you access to tools for constraint-based modeling, model simulation, parameter estimation, and also learning unknown mechanisms with neural ODEs and sparse identification of nonlinear dynamics. So let me first start with constraint-based modeling with COBRA. What we can see here on the left side is that it just takes one line of code to import an SBML model, and then another line of code to perform flux balance analysis, and you get all your fluxes. But like I said earlier, what Julia does well is it scales well to use multiple workers. So even if you don't know parallelized programming, you can just say, I use the distributed package, add any number of processes I want to use, load the necessary package on all the processes, and then run whatever analysis you want, for instance, flux variability analysis. And my colleague Mirek, who developed this COBRA package, tested how well Julia actually, or how well COBRA actually scales to multiple processes. And to this end, he used metabolic models of not just one organism, but of communities of up to 50 organisms. And he compared COBRA with COBRA. And you can see that for a relatively low number of CPUs, they perform roughly equally well. But if you want to do analysis on very big models, you might want to use a larger number of CPUs. And this is facilitated with COBRA, and it actually scales reasonably efficiently until and beyond 100 CPUs. Okay, the second use case just highlights CellML Toolkit, which allows you to import CellML models. Here we are looking at a model of the O'Hara-Rudy left ventricular model. And we can again import the model in just one line of code and then convert it into an ModelingToolkit ODE system, which, like I said, is the entry point into the SciML ecosystem. So you have all SciML tools at your disposal. At this point, we are just solving the model and plotting the solution, which is shown here on the right-hand side. The third use case is parameter estimation. And here we are looking at approximate Bayesian computation of a Lotka-Volterra model. But of course, again, there are other optimizers you could use in the SciML ecosystem. This uses SBMLToolkit, but there's one important thing to note. So SBML models allow you to specify a lot of things, and we don't support all of them yet. So we recommend to first check if your SBML model is actually supported, because we don't support constraints, we don't support events, and we don't support rules yet. But if this passes, you can import your model and simulate it. And here on the right-hand side, we have not only simulated the model, but also created an artificial data set for approximate Bayesian computation with a bit of noise added. Then if you want to do your approximate Bayesian computation, you first have to specify your priors, and then you can run your MCMC chain. And what you can do then is you can plot the covariances of your parameters. Just as a brief sanity check, what are the ground truth parameters? This is shown here, and they roughly do correspond to what we get as an output here. Of note, these are of course the modes, and these are of course the means, but this is just a sanity check. This already brings me to the final use case, and I think this is the most interesting one, which is learning unknown mechanisms with neural ODEs and sparse identification of nonlinear dynamics. And it was at the beginning of COVID when Lin et al. Created this SEIR model of COVID spread. So S are the susceptible people, E are the exposed people, I are the infectious people, R are the recovered people, and then they have also variables for the total population, for severe cases, and for the cumulative cases. And an interesting thing about this model is that they have this term, which describes the animal to human spread, and this term here, which describes the human to human spread. But you can see in this term, we don't have beta as a constant, but beta as a function of t, and this shall describe governmental and psychological factors. So obviously, introducing such governmental and psychological factors into a mechanistic model is very difficult. So what one could do is, basically that was the idea of Chris Rackauckas, a colleague of mine. What one could do is that we replace the whole system with a neural ODE. So the way how neural ODEs works are that you say, okay, the time derivative of my states equals a neural network of my states. And if we go one slide back, we see that we have 7 states here. So we have 7 input nodes as states and 7 output nodes as the time derivatives of the states. And the good thing is, so the reason why that works is that neural networks are universal function approximators that can literally approximate anything. So we can have a look and say, okay, we train our neural network on 21 days of simulated data of pandemic spread, and then try to extrapolate this into the future. And if we do that, we see that the neural network approximates the training data quite well, but doesn't really extrapolate well into the future. And the reason being, the disadvantage of a neural network is that it can approximate literally anything. And here it approximates a function that does a good job for the training data, but not for extrapolating. But we can say, okay, why do we actually have to try to approximate the whole system with a neural network if it's just one term that we are unsure about? So we can say, okay, we just replace one term with a neural network. And for that, we can use a smaller neural network, which is less flexible and might extrapolate better. So what we have here, what we've done here is our neural network has just one output node that describes the time derivative of our susceptible people. And we can even go a step further and say, maybe we have expert knowledge that tells us that not all 7 of the variables are affecting this rate. It might just be 3 of them. And then we can create a neural network with just 3 input nodes. All right, we can train again this neural network on 21 days of simulated data and see what the output is on these 21 days. And then also have a look at how this neural network extrapolates into the future. And this already does a bit of a better job. We can extrapolate up until 14 days into the future. So on the next slide, I would like to show a different approach to neural networks, which is sparse identification of nonlinear dynamics. And the way that works is that you have as an input the time derivatives of your system states. So the rows here are different time points of the simulation. And what you can do is you can say, let's focus just, for instance, on the state X in blue. What you can do is that you can say, okay, time derivative of X is a matrix of candidate functions times a vector of coefficients that tells how active different candidate functions are. This is then a linear regression problem, and you can try to sparsify that using things like L1 regularization, and then just select a small set of your candidate functions. And you can do this for all states and thereby try to identify the system you started with. Problem with that approach is, again, it's very data hungry and we have just 21 days of data. But yeah, this basically leads to the assumption that we'll just get garbage out. But we've shown, so on the slide earlier, I've shown that we've approximated not the whole system, but only a subpart with a neural network. So we can put this neural network into SynDI and try to see what it has, what this neural network has actually learned. And the thing that it has actually learned is a very simple equation consisting of just 3 terms. And then we can go ahead and say, okay, we take these 3 terms or this equation and substitute them into our whole system and have a look how this extrapolates now into the future. And this is now doing a much better job and extrapolates, well, up until, day 60. Okay, so in a sense, just to wrap things up, all that we've really done is we've developed CellML and SBML importers into Julia, which give the systems biology then access to packages for constraint-based modeling, ODE simulation, parameter estimation, scientifically informed machine learning, and some others for plotting bifurcation diagrams, creating graphs of your system, etc. So the major limitations are that our packages have no export to SBML and CellML yet. We have not yet implemented supports for SBML constraints, events, and rules. There's also no PTAB support. If you want to have PTAB support, you can have a look at SBML to Julia, but this only works for discretized then optimized optimization schemes. If you want to have a look at our packages, they're all hosted on GitHub in the organizations of the Luxembourg Center for Systems Biology and SciML. And if you want to get involved, you can always create pull requests to our packages. And I would especially recommend joining the SysBio SciML channel in the Julia Slack workspace. You can find the link here in this QR code, or also on my profile for the Combine conference. With that, I would like to thank all of my colleagues, Mirek, Moza, and Laurent, who've developed SBML.jl, then Anand, who helped me with SBMLToolkit, then Sharia, who developed CellMLToolkit. I would also like to thank Sam and the whole Julia SciML community for their general advice, and especially Chris Rakaukas, who came up with the use case of scientific machine learning that I presented in the last few slides. I would also like to thank my funding body and the organizers of Combine 2021 for giving me the opportunity to present, and I'm now happy to take any questions.